Good evening, folks. My name is Amit. This is week 3 for GATE Physics live sessions. We'll wait for a few minutes and then we'll begin. In the meantime, if you have any questions regarding the last class or anything in general, you may ask. We'll wait for like 3 or 4 minutes and then only we'll begin the session. So if you have any comments or questions, please ask away now. All right, we'll begin now. So I'm sharing some details in the chat box, my email ID and the link for YouTube channel, the channel name, sorry, and then the link for YouTube channel. So in case you may want to watch the videos later, I usually after taking a live session within a 2 or 3 days or maybe 4 days, I upload the session that we had conducted. So if you want to go through some concepts again or some questions again, feel free to do so. And the email ID is for the purposes that you may want to write to me in case you have any doubts or anything you want to comment in general. um, I'm audible, right? I should have asked that beforehand. Am I audible?
Yes, sir.
Okay, so I'm going to present my screen now. Just hold on a second. Okay. Are you able to see the screen? Can you see the presentation? Anyone?
Yes, sir. It's visible.
Okay, so we'll start. This is Gate Physics live sessions. Today's third week for this round. My name is Amit, and in the last classes we were discussing. Just hold on a second. In the last two sessions, we had talked about special theory of relativity. This week we'll continue, and maybe 2 or 3 more weeks after this, because there's a lot of different topics in this topic. Usually, all the questions revolve around just two formula, and the concept is also very simple. So that's how I am emphasizing its scoring, not just for GATE, but even for other exams that you may want to write, like JEST or any TJRF. We'll we'll get started. We had talked about special theory of relativity, that this relation between the space which you defined as x, y, and z, and time, we denoted by t, and we had been following this configuration, if you remember: x comma y comma z semicolon t. and we are neglecting gravity here, and these are the twin concepts that special theory of relativity is built upon. The first is that laws of physics will remain invariant in inertial frames, and second, speed of light is same for all frames. So these are the twin postulates, or twin very basic building blocks for special theory of relativity. What do we mean by laws of physics? It is like the laws like change and conservation of momentum, conservation of charge, conservation of energy. We'll see some of them in the maybe not today, but in the next class definitely. Second thing is, what are inertial frames? Inertial frames are nothing but where you're observing something, the frame of reference with zero acceleration. This is important. There is no acceleration. This means the frame can be at rest or at constant velocity. Acceleration or time dependent velocities are not allowed. We had seen that velocity should not be a function of time. Should not be t square, t cube, square root t sine t. No, velocity should not be a function of time. Right, then there are some key terms which I keep on using, and which you will keep on hearing or reading about them. The first one is the observer. So what is an observer? In inertial frame, we saw inertial frame is which is not accelerating. So here is a blue frame with the observer is sitting at origin, and it's measuring the three-dimensional space x, y, and z. Right, and obviously a time coordinate is also there. Similarly, there is another frame. Let's call this frame S prime. Let's call this frame S. We'll keep on following the same notations. S will be at rest. S prime is moving at a constant velocity v in positive x direction with respect to the frame S, and here the observer is sitting at O prime. So what do these observers do? So they capture some events. So let's say there's an event P happening at some coordinate xp, yp, zp, and tp. This is what we call an event. An event can be anything, like bursting of a tire, clapping your hands, flashing of an LED. Anything and everything is an event. Similarly, correspondingly, the same event will be here, but the coordinates will be different. It will be xp prime. Note everything is primed. Yp prime, zp prime, and then finally tp prime. Note the notation: space coordinates, semicolon, time coordinates. And this is basically everything is derived as far as the mathematics is concerned from this. There's an entity called space-time interval, which we denote by delta S. It is invariant across different inertial frames. So for instance, delta S, if we determine in this frame, will be equal to delta S squared in this, delta S squared in this frame will be same as delta S squared in the S prime frame. And what exactly is the mathematical formula for delta S? Is it denoted by this? This is the time interval, we can say. C, speed of light. Delta T is the time interval between two events. So the first event is P. Let's say second event is Q here. So it will be XQ, YQ, ZQ, TQ. Or you can say x1, y1, z1, and then x2, y2, z2. So similarly, and delta t, delta x, delta y, delta z are the respective space intervals and time intervals between them. This is how it's calculated. This is the formula for this. And based on this, we have obtained some transformations. What kind of transformations? We saw Lorentz transformation. So let's say we are in a non-relativistic world, means that velocity, this velocity v, let's say in this case, is v is less than c. C is 3 into 10 to the power 8 meter per second. So here we have seen this in high school physics, or maybe in your bachelor's or master's also. This is what we have usually encountered. Time does not change, while the x coordinate in this prime frame will simply be shifted by a vt component. It's not the same case when v is close to c, right? When it's close to c, it's not the same. And what remains conserved? Space-time interval remains conserved. We solved one problem in the first week, and this is how Galilean transformation is replicated in the world of special theory of relativity. So you note that t prime is not same as t. It is now given by this factor, this formula, and v is the speed of this frame, of the second frame. T is the time in the first frame, and gamma is a component which we have obtained like this here. So you see, if v is less than c, then gamma will tend to 1. Right, and all the formula will come back to this. But this is called the Lorentz transformation. In relativistic world, Lorentz transformation. Note, this is all in inertial frames. Right, then we have also seen sometimes we are given the coordinates in the S prime frame, and we need to know the coordinates of an event P in, let's say, this frame, the S frame. So how do we do that? So in order to convert from this frame to this frame, we use something called the inverse Lorentz transformation. You know that. Let's just, we are determining time and space coordinates, and we are given the time and space coordinates in the S prime world. This is and we had solved a couple of questions on this in the last class that we had, the last session, right? So moving forward now from today, now we begin our fresh work. So today we are going to build up on we had talked about in the last class. So this is frame S, this is S prime again. Now last class session we had done time transformation and space transformation. Now a natural progression is that we know velocity is dx over dt differential, or let's say delta x over delta t. So if we know delta x, we know delta t, we can determine the velocity. So let's assume that there's an object here. Okay, let's call this object A, and it's moving with, let's say, in this direction, in this. So this observer is seeing that this object is moving in this frame, let's say some in positive x direction with some velocity ux, right? And again the same object A will be seen here, but it may have a different velocity ux prime. So we want to know what is this velocity, right? I repeat the problem. In this frame, in the first frame, an object A is moving with some velocity in positive x direction ux. Why I am taking positive x? Because to keep it simple, in the end we'll generalize this, and we want to know what is the velocity in the S prime frame for this same object, where S prime frame is moving at a constant velocity v with respect to the rest frame S here. So we know the known velocity is ux. Ux is the velocity that we know. I told you it's in positive x direction with some constant, right? And we want to determine this velocity ux prime. So if you see the formula, ux prime is delta x prime over delta t prime, right? So and we know delta x and delta t, and we can determine delta x and delta x prime and delta t prime. How? If you use the Lorentz transformation. Note, Lorentz transformation transforms to prime coordinates if we are given the non-prime coordinates. So what we'll do is that delta x prime will be nothing but x2 prime minus x1 prime, and I'm just plugging in this formula. So you can say this will be gamma x1 minus vt minus gamma x2 minus vt. So I've just clubbed the gamma x, so it will be gamma into x1 minus x2, x2 minus x1. So this is like this, right? Minus v times t2 minus t1. So this is t2, this is t1, right? So this is what we'll get. Similarly, delta t prime is here. Delta t prime I am writing as t2 prime minus t1 prime, right? So it will be gamma times, again it will be delta t minus v delta x over c square. And if we take delta x and delta t are infinitesimally small, then this delta gets transformed to differential like this. The form changes, rest all remains the same. And what I'll do is that I'll put these values here. So that's what I'll do. So I'll put gamma, the value of dx prime is dx minus v dt over gamma dt minus v dx over c square. Gamma gets cancelled. What I get is dx minus v dt numerator, and denominator is dt minus v dx upon c square. And if I divide everything by dt, numerator as well as denominator, so I will get dx by dt minus v, okay, divide by 1 minus v dx over dt over c square. Now dx over dt is nothing but ux. We know this is the velocity that was given to us, right? So I'll replace that here, and if it then you will get this form, ux prime equal to ux minus v. Note it was okay, what I'll do is I'll write it here. So it will be ux, dx by dt was ux minus v divided by 1 minus v times ux over c square. Dx by dt is nothing but ux. So this is the formula that we have gotten of ux prime, and which is the same which is in this red rectangle. So it didn't use anything. It's just the only concept we used was the Lorentz transformation formula, which we had seen earlier. Now based on this concept, now we'll try to solve a problem. This problem was asked in GATE 2013 exam. The problem says that an electron is moving with velocity of 0.85 c in the same direction as that of a moving photon. The relative velocity of electron with respect to photon is. Now these it's important to identify that this is a problem of nuclear particle physics, or it's a problem of special theory of relativity. So whenever you see the speed of light being mentioned, right, And if you see these terms like relative velocity, same direction, most likely, and photon, most likely it will be a problem of special theory of relativity, not of nuclear particle physics. If you see enough problems, you'll realize that. Right. But before we solve this problem, there are few things we must check. First, all the theory that we had talked about was based on that inertial frame. So we must see whether this is inertial frame or not. So there is some frame, right? There is some frame which is measuring the velocity of electron as 0.85 c. So that frame is our S frame, right? That frame is our S frame, where it's measuring that this electron is moving and no direction is given. Let me assume it's moving in this direction at 0.85 c. Okay. Secondly, it says that then the photon is also moving. So let's say that is the S prime frame. So this is the S prime frame. This is the photon frame. So photon is moving. So this is moving at a speed c with respect to this rest frame. This is our rest frame, and this is our photon frame. Okay. And now we want to know the speed of electron with respect to photon. That means the electron will be here somewhere, right, in this frame. And we need to know ux prime. Ux was the velocity in this frame, rest frame. We need to know the velocity of electron in this new frame. Since we have assumed one frame to be rest frame, so it's obvious that frame is rest frame, that is inertial. We talked about inertial frame is whether the frame is at rest or constant velocity. So this frame is at rest, right? That's why it's called rest frame. This frame, the photon frame, is moving at a constant velocity c. So this is also inertial. So we see inertial frames, yes, both the frames are inertial. Second, the moving frame, this means this photon frame, what is its speed and direction? No, the question is silent about speed and direction. It doesn't talk about. But we know photon moves at speed of light. So we know the speed, that is, this speed is c. What about direction? The question is silent on direction. If the question is silent on direction, we'll assume that it's moving in positive x direction. Why that? Note that all the formula that we have derived from positive x. Now, most of the problems that you'll encounter are in positive x direction. So it's easy to solve the problem. You can take it positive y, negative z, radial, whatever you want. It will not change the form. Next, and this is important, the number of dimensions. So the question is silent on number of dimensions, says only moving. So if nothing is given, assume dimension is 1. What do I mean by dimension? That means you need x, y, or z. How many of these you need? So we need only x. There's no two-dimensional motion. So there's only one. There's only one. We assume it's a one-dimensional motion. Very simple system. So this was our system. Now redrawn it here. So remember, this was our rest frame. The frame S. Okay. Here is our electron. This is the electron, and it's moving. Again, I've assumed it's moving in this direction at, what is the velocity of this electron? 0.85 c. This was given in the problem itself. Okay. So, right. And this is the second frame. This is the, what I call the photon frame. This is the moving frame. S prime frame, which we used to call, and it's moving at a velocity. Photon moves at a velocity of light, so v is constant, which is c here, and we need the electron will be also in this frame. So let's assume the electron is here again. This is the electron, and it's again moving in this direction. So we'll need to know ux prime. What is the velocity? That was the question. The questions asked velocity of electron with respect to photon. In other words, we can say velocity of electron in photon frame, or velocity of electron in S prime, which we denote as ux prime. And we know the formula of ux prime, which is written here. Note, ux was the velocity of the object in rest frame, which is given 0.85 c. V is the velocity of moving frame, which is, this is given as c. Ux was 0.85 c. Ux prime we need to determine, and again we know this term. So I'll simply plug in the values. So ux is 0.85 c, v is c, 1 minus 0.85 c into c over c square. So c and this c square gets cancelled. In the numerator you will get minus 0.15 c in the denominator you will get 0.15, because 1 minus 0.85 is 0.15. You will get minus c. Very interesting. So what I get that from, if this photon, this means the photon which is here in this O prime, sitting at O prime, will see that electron is moving at a velocity of 3 into 10 to the power 8 meters per second in opposite direction. Note this negative sign. So this means electron is actually traveling in this direction, left direction, you can say, right? So this is an interesting thing that we notice. So first we'll see that we'll see this is an option. So option B is correct one. But there's a trick here. We should not have solved this problem. So any velocity with respect to a photon frame. So let's say this is the photon frame S prime. Photon frame moving with velocity v equal to c. Right. So let's say there's any arbitrary object A. Its velocity is ux. Let's try to determine its velocity is ux prime here. Let's say its velocity is ux in this frame, rest frame. So if I use the formula ux prime equal to ux minus v over 1 minus ux v over c square, v value is c, it will be ux minus c over 1 minus ux c over c square. 1 gets cancelled. You will get ux minus c upon c minus ux into c. You will get minus c. What are we seeing? That this photon frame will see everything moving at negative c velocity. This means this photon will see everything is moving away from it at 3 into 10 to the power 8 meters per second. This is a direct, this might be asked directly in match the following or something, that what is the speed? Question is, what is speed seen by a photon? Yes, seen in frame of photon. Seen in frame of photon. It will be always be c in negative direction, but if the speed, so we ignore the direction, so magnitude will always be c. This is a trick you can remember. You can solve the formula any way you wish. I prefer to solving, but in case it's a match the following, this is a straightforward thing to remember. So I'll pause here a bit because I talked about one formula here, and I'll revise what we went through. So what was given to us, that electron is moving at a velocity of 0.85 c. So we assume that in some rest frame, this is electron moving at ux equal to 0.85 c. This is the frame S. This was the frame S prime, or the photon frame. This frame itself is moving at constant velocity equal to c. We assumed only in the x direction because the question was silent, and then we simply applied the formula of ux prime, this formula, and we solved this problem. I'll pause for a minute here, and then I'll let you digest this and ask me if you have any doubts, you want me to repeat something. I'll pause here for a bit, and please let me know what you need. I'm also checking the chat box if there are any comments, so please ask away if you have any comments, you want me to repeat something, anything, or if we are good to go, we can go ahead. I need to re-emphasize that we are just building on the last class where we talked about the delta x and delta t. This is velocity is nothing but delta x over delta t, and this is the formula we derived, and we solved this problem. And these are again very straightforward problems, just simple formula based, very simple. Okay, if there are no comments or questions, anything, anyone?
Sir,
Yeah.
sir, can we do the same problem by S frame as the photon's frame? Can
Okay, you want the S frame as the photon's frame. That's what you want? Did I hear that correctly? S frame is photon's frame, right?
Yes, yes.
Okay, so let's try that. I don't know. We'll try it. Let's do this. So this is the frame S. Okay. This is moving in this direction, let's say, at constant velocity equal to c. Okay. And this is one S prime frame. This is at rest. And we know that the velocity of electron in this frame is 0.85 c, which we usually denote as, so in this case I will denote it as ux prime, because note we are in prime frame. That's what you had asked me to do, right? So but note that
So it will come minus c only.
sorry,
It will come minus C, sir.
It will come minus. Yeah, see, formulae and representation frames, it's just for our ease of solving. The physics will not change, right? So you solve it yourself, correct?
Yes, sir. If we just sit on the photon and observe the
Yes,
electron,
yes.
it will come
So
in
so
negative directions.
that you very good point you raised. If you sit on photon, everything will be visible to you as at moving at minus c. As simple as that. That's what I told you. If you can remember this, if you are sitting on a photon, everything will be minus c. Simple, very straightforward, right? So if you solve this, you'll again get the uh, same thing here, right? Right.
Sir, what if we have two photons
Uh-huh. So I did the thought.
and
I did this thought experiment actually. That what if we have two photons? I'm sitting on one photon, and another photon is sitting, and you are sitting on another photon, and we are traveling from the sun. Okay, what happens? So if you are traveling in the same direction, right? We'll be at rest. We'll be at rest with respect to each other. This is like we are sitting in the same bus, right? On the opposite sides, right? And we'll see that we are traveling in the same direction. You will be at rest with respect to me. What happens if you are traveling from sun, let's say in the positive x direction, I'm traveling negative x direction, right? What happens then, right? Because speed of light cannot be violated, it has to be c. That's the second postulate, right? We saw that the speed of light is c. That cannot be changed.
sir, but by the formula it's coming 0 by 0, which is indeterminate form.
Indeterminate form, yes, you have to apply the limits in that case. So what we'll do is that if I remember the formula, it was ux minus v upon 1 minus uxv over c square, right? This was the formula. So let's drop this c term, okay? Or let's just keep it. It will confuse you. It might confuse some people. So what you are saying is that ux is c. That's the first photon, and v is also c, and we need to find the speed of photon with respect to another photon. So this case is fairly simple. So I see c minus c upon 1 minus c into c over c square. What you are getting is 0 over 0 form. That's what you were saying, right? Okay, so let's not do that. Let's put if I remember my 11th class physics correctly, 11th class mathematics correctly, what I'll do is that I'll do this limit ux and v tends to c, okay? And I'll solve this ux minus v over 1 minus uxv over c square. Okay, so if I solve this limit ux comma v tends to 1, and I'm dropping c, so it will be ux minus v over 1 minus ux into v. Essentially I have taken c common and dropped it, right? So what I'll do now is
Use the LH rule.
so no, see, both the terms are the same. So I'll do is this. No, I cannot do that actually. So what
You can use LH rule.
using?
And
Yes,
hospital
I
rule.
remember. Yes, there was that rule. I think we differentiate. I'm forgetting. Sorry, man. So what we do?
Differentiate in numerator and denominator both.
So what will happen is that, so I think in numerator you can get constant, right? But in denominator you will, because if you apply that it will be something like 1 into v, there will be negative sign, minus 1 into ux. You will get something like this, and numerator you will get a constant, right? So if you do this, so it will be, I think, 1 minus 1, and this will be 0 over some constant value. Note that v, this is 1 into v and 1 into ux, so maybe you'll get 2c. 0 upon 2c will be 0, correct? I did it correctly, right? I hope. I have forgotten the L'Hospital rule, but yeah, it's differential, and it will take this form. What I was going to do, I was going to do some long method of taking common and whatnot, but yeah, essentially using this formula you can get that two photons, when they're moving in the same direction, they will be at rest with respect to each other. Now what happens if they're moving in opposite direction? I don't know what will happen then, because then I don't think this top term will collapse, because then it will be a plus sign, and then it would be okay. Let's do that. Let's not run away from a problem. I'm writing this again. So this time, so ux value would be c, let's say, and this is minus c. Okay, so I'm writing the limit at ux goes to c and v goes to minus c. So let's see what happens then. And again, if I apply the L'Hospital rule, so it will be, I think 2 will come in the numerator, right? If I'm not wrong, 2 will come in the numerator, and again this will be a plus sign. Correct. So we are saved. So we'll get in the denominator. So first we keep this and differentiate this. So what we'll get is, I think, v over c square, and then we keep this and differentiate the other. We'll get ux over c square, right? So it will be 2. Note that, so 2 c square over v plus ux. This will be 2c square. We put the limit back, 2 by c. Sorry, 2c. So it's coming out to be c. You understood it, or should I repeat? Is it clear? I'll repeat.
Clear, sir. Sir, what if we have a frame which is moving with c speed, and we have a rest frame, and an object, or maybe you say an electron is placed in that c frame, and which is moving at some c, say point at c, and if we observe it from rest frame, what will be, means will it violate the
No,
c speed, or
no, it will not. So you asked if an object is moving in prime frame, what is its velocity in rest frame? That's the question, if I understood correctly. Well, you read my mind. This is the next topic of discussion here. Inverse velocity transform. So this time what we know, this is the known velocity, right? This means there is some object here A which is moving at ux prime. We know this velocity, numerical value we know, and this frame is s prime. Again, this frame s prime is moving at some constant velocity v with respect to this frame s, and we want to determine this object's a velocity in this frame. Ux is unknown, ux prime is known. Okay, we know this was a question. We are going to solve this. So what will happen again? So we need to know delta x and delta t, and we'll be fine, right? How do we know delta x and delta t? We'll use inverse Lorentz transformation, right? So we know delta x is x2 minus x1. So if I put x2 minus x1 here, it will come delta x1 prime plus v t1 prime minus, sorry, I always do this, minus x1 would be gamma x1 prime plus v t1 prime. You subtract the term, you rearrange, you will get this form, gamma delta x prime plus v delta t prime. Similarly, for delta t, it's t2 minus t1. You'll get gamma t1 prime plus v x1 prime by c square, and you again rearrange the terms, you'll get this term. This is nothing but just putting the values and just taking the x terms together and t terms together. You'll get this. Now this is in delta. You can say this is the macro picture. If we take a differential element, delta gets transformed to d. We just talked about it, and it will take this form. Now what I'll do, I'll simply put this here. Ux is dx over dt, so I'll put this value here, gamma dx prime plus v dt prime divided by gamma dt prime plus v dx prime over c square. Gamma gets cancelled. Again I take dt prime common from both, so it will become dx prime over dt prime plus v, this is the numerator, divided by, I have taken dt prime common here, plus v by c square into dx prime over dt prime. Now if I solve this, dx prime by dt prime is nothing but ux prime, so this will be ux prime plus v, this is the numerator, denominator would be 1 plus v times ux prime over c square. Dx prime by dt prime is nothing but ux prime, we know this. You'll get this. Interestingly, this is the same form as before. Note that, I'll write it here. So that form was ux prime minus v over 1 minus ux prime, ux into v over c square. It is the exact same form, the signs are reversed, which makes sense because if you compare Lorentz and inverse Lorentz transformation, we'll go to that slide. This. So what is the difference between inverse and Lorentz and inverse Lorentz transformation? Just the sign and the prime change, right? Prime become non-prime and so on. The same logic follows in velocity also, right? You see this, when we want to, if prime velocity is known and we want to know the rest frame velocity, the signs are plus. And in the other case which you saw earlier, if we know the rest case velocity of the object and we want to know the velocity of the object in some moving frame, we get negative signs. So I hope this answers your question, and you asked a very prominent, very interesting, very relevant question in fact, which led me to solve this. Is it fine? Does it answer your
Sir?
does it answer your question which you were asking?
Yes, sir.
Okay. Now what happens is that again a problem was asked based on this transformation. That is, this velocity here was given and we needed to find the velocity here. So if you see the gate, actually what they do is that they try to cover the topics. So both these questions are covered. Most likely they'll go for some different things. We don't know, but doesn't matter. We'll prepare the way we know. Let's read the question carefully. Okay, a spaceship is traveling with velocity 0.7 c away from a space station. Okay, so let's say I'll draw this space station here. Note, space station is at rest. Usually it may be geosynchronous. I'm not, need not always be. So so what's happening is that, so we'll assume space station to be at rest, which is a rest frame. So this is our space station frame. It helps if you label the frame, because then you're not confused. So space station is at rest and it's saying that there is a spaceship. Okay, so this is the spaceship frame. So spaceship will move around in the space and we'll assume it's moving with a velocity of 0.7 c. It's given here from the space station, so it's moving in this direction. The spaceship ejects a probe. Okay, so here is a spaceship. This is the spaceship and it ejects a probe, like for some experimental measurements. So it ejects a probe with a velocity of 0.59 c. So the probe is ejected in this direction. So I'm calling this probe P and its velocity is, since we are in prime frame, we'll call this as 0.59 c, opposite to its velocity. So that's why the direction is in this direction. Now a person in space station, so a person is sitting here in the space station, our observer O, our good friend, sees the probe moving at speed xc. So this person here sees that the velocity of this probe is x times c and we need to find the value of x. This is a numerical answer type question. We'll find our answer and then round it off to 3 decimal places. This is a practice you must remember, because sometimes marks are not given if you don't round it off properly. One of my friends suffered due to this. Right, again we do some pre-checks. We make sure the frames are inertial. So we assume space station to be at rest. This means it is inertial. So frame 1 or space station station frame is inertial. Frame 2 or the moving frame, which is a spaceship frame, it's moving at constant velocity. This is also inertial. We are satisfied. So all our STR formula are valid. Second, what is the speed and direction of moving frame? So moving frame was spaceship frame. We know it's moving with velocity 0.7 c in a direction. We know the direction. We have assumed in this case to be positive x. I told you why positive x, because usually we derived a formula in positive x. Again, number of dimensions, nothing is given in the problem, so we'll simply assume number of dimensions is 1 and we don't see any like x or y component. If we saw x or y component, then we would have thought about more than one dimension. In the last class, if you remember, we had solved one problem where a frame was moving in y direction. So you might want to see that if you need to know that the game of dimensions here. Right, so all our formula are valid and we are happy, and we'll simply go ahead and plug in the formula. Right, so I'll again draw the frame. This is the space station frame, an observer sitting here. This is the spaceship frame and this velocity was given as 0.7 c, if I'm not wrong. Yeah, 0.7 c, and there is a probe here. We call this probe P and it's moving at a velocity in this direction with ux prime equal to, what's the velocity, 0.59 c, 0.59 c, and we need to find the velocity of this probe. Again this probe P here as xc. So this is nothing but we denote as ux. So we need to find the value of ux. V is given as 0.7 c and ux prime is given as 0.59 c. Right, I'll just simply plug in the formula. Ux prime is 0.59 c plus v is 0.7 c divided by 1 plus ux prime is 0.59 into 0.7. Oh, there's a c in c, so c times c over c square. These gets cancelled. it will come out to be 1 point. Oh, sorry, it's in opposite direction, so it will be
Next is
minus point.
negative sign.
Yeah, sorry, so my bad. So it's minus 0.59, so it will come out to be 0.11 c. 70 minus 59 is 11, and this will come out to be I need my calculator, just hold on. So this will be 0.59 into 0.7, this will be 0.413, so this will be 1 minus 0.413, and 1 minus 0.413 is 0.587, this is 0.11 c over 0.587, and we'll get our answer as 0.1874 c. It's much more, the fraction is much longer, but remember 3 decimal places, right? I took it off to 4 so that we can round off accordingly. So what I got was 0.1874 c. Ux prime was 0.1874 c. First we need to round off to 3 decimal places so that we can drop this 4. So Ux prime will come out to be 0.187 c, which is equal to xc. This was given. So the value, comparing the value of x would be 0.187, which will place here. I'll again re-emphasize, please round it off. Usually the answer key gives some leeway, but I have seen in one of the answer key it's very precise. If it's 0.187, it is 0.187, not 0.188, 0.190, nothing. So try to be precise. You anyways have calculator on your screens. At least in GATE, I think NET, you are allowed to carry calculator if I'm not mistaken. Yeah, that's that. So again, so we solve this problem. Again, straightforward problem. 2 frames. One was the station frame, which coincidentally was stationary. Second was the shift frame, which was moving at a constant velocity. There was a probe. We were given ux prime, that is the velocity of probe in moving frame, and we were required to find the velocity of probe in stationary frame. Simply used a formula, and we got our answer. So that's that. And so this covers both the aspects, the velocity transformation, and that is from what is the velocity in moving frame if rest frame velocity is given, and vice versa, what is the velocity in rest frame when the moving frame velocity is given. So that covers both the aspects. We saw 2 questions. I'll again pause a bit here. So if you have any comments, please raise any questions. I'll pause a bit. If you want me to repeat, please say so. Just hold on a second. All right. Okay. So if no comments, then we'll move forward. So this actually completes the transformations part. Now we can see what transformation 3D looks like. Note that we talked about 1D. We talked about 1D only now. So we know this is the known velocity. Ux, Uy and Uz were known velocities. The energy of particle remains same. Total energy will remain the same. Yeah. The thing is, again, there is a mass energy equivalence here. So we will visit that in the next class. I think I forgot. In the next class, we have this mass energy equivalence where we talk about energy. See, the thing is, I'm gradually building. First, we talked about distance and time. Then we divide distance by time. We get speed. To get to energy, you need to talk another entity called mass, because if let's say for the sake of discussion, the kinetic energy is half mv square. This is what we have read. So this class we have seen what is velocity, how does velocity transform. Soon we'll see how does mass transform, right? And then we can comment on the energy. So I'll not comment anything now. We'll see it together. Just like today someone brought up when we got the inverse velocity transform, just like you raised it, we'll see the mass transformation, right? And we need to determine in this case the unknown velocities in 3D space. So what I'll do again, I'll invoke my Lorentz transformation, because we need to know the primes with the non-primes are known. So we use the Lorentz transformation, and then again I do this thing which we saw in delta x. Note that now delta y is interesting. Delta y is y2 prime minus y1 prime, and y2 prime is nothing but y2, because we are moving in x direction. Note that. So delta y prime is nothing but delta y. Similarly, delta z prime is nothing but delta z, and you again put in this formula. So I'll try to solve for ui prime. Okay, it's dy prime over dt prime. So again the differential components will come, so it's not big deal. So it will be dy divided by dt is nothing but gamma dt minus v dx over c square. I'm using this formula for dt and putting it here. So you take dt common, take it up, so it will become dy by dt divide gamma 1 minus v by c square dx by dt. Okay, so this will be dy by dt. Okay, so we know dy by dt, do we? Yeah, dy by dt is uy. So there is a object here which is moving in ux, uy, uz like this. Similarly, the same object is moving at ux prime, uy prime, uz prime. So dy by dt is uy divided by gamma is there. So 1 minus v by c square dx by dt is nothing but ux. We know that. So we got this formula uy over gamma 1 minus vux over c square. This uy over gamma 1 minus uxv over c square. Similarly, you see y and z are equivalent, so you can also derive for z here. Why I do this, why I did this is that usually you will not have questions in gate of 3D, but in some other examinations there may be. I'm recalling one question where I think it was in TIFR graduate studies. I'm forgetting the name of the examination, but there was one in which it was in 2 dimensions. So just for the sake of completion, when we have come up to this point, I feel that it's good that we complete the topic. There's no holes left, there are no gaps left, and I am fully equipped to solve the problems. So this is the summary for this 3D velocity transformations. We saw this formula earlier only, ux prime. We saw this, right? And for inverse velocity transformation we'll get ux as this. We also saw this formula. It's just a uy and uy prime and uz prime we determine in the last slide. And similarly, I told you that you just flip the signs. I was never able to remember the formula for ux. Somehow I remembered ux prime, so I just simply flip the signs, so you can see that. So that's that. Even if you forget, it's easy to derive. That's why I showed you the derivation. It's fairly straightforward. So that completes the velocity transformation, right? But this very interesting thing with this is the actually the practical impact that we do see in real life. Even though we move nowhere, I told you this str becomes relevant when v is very close to c, like 0.1 c, 0.2 c. But even though we are not close to c, the astronauts which are there in International Space Station, right, they spend considerable amount of time there. They age differently from us, although that difference is in milliseconds, so it's irrelevant. But the thing is, we have scientific measurements which see that those people age differently than the humans living on the earth. Okay, so there is a difference. So this is not something like which is completely in theoretical regime. We do see its impact, and we see, I told you, we see its impact more prominently. I think the first class we talked about more prominently in particle physics, because when particles like neutrinos, they are collided in the Large Hadron Collider in Europe, CERN, they do those experiments. So these things do come in very handy there, right? So there are two concepts related to this. First is length contraction, second is time dilation. We'll see them one by one. Today, first we'll see the time dilation. So first we need to define time. It's a very, I mean, we have taken time for granted. We always see the clock and we know the time. But for this discussion, we need to define time, right? So there is one observed time, means which this observer, our observer O, sitting in this frame S, is measuring some time. So how does it measure it? Observed time is measured in observer's frame, which in this case is frame S, for co-local events. Now, what is this term co-local? Co-local means this. So I'm measuring at the same position. So what means is that, let's say this is some position x1, y1, z1, and let's say I take a photo at time t1, right? So let's call this photo A. Again, I take another photo B. The object stays there, it's not moving, at a different time t2. This is what I mean by co-local. So I am taking two different snapshots, okay, at the same spot. I'm taking the photo of the same location, exact same location. Space coordinates remain the same, only at different times. Such events are called co-local events. Co-local, they are the same, delta x, right? And this will be the time observed, t. The time difference that you will observe between the second photo and the first photograph is your time, noted by capital T here. Now what I want to do, as we always do, we are moving in some frame V with a constant velocity. See, note both these frames are inertial. This is S prime frame moving the positive x direction, the constant velocity V, and we want to measure, right? We want to measure in, so usually there is sometimes there's an object, like we saw in the last example. This was the spaceship, right? This was the spaceship and this was the space station. So it might happen that the persons sitting in the spaceship might want to measure the time, their time. So what they'll do, in their own wristwatch, they'll measure t2 prime minus t1 prime. Note the location would have shifted, but the events will remain the same. So it will be x1 prime, y1 prime, z1 prime, comma t1 prime, and another photo taken at x1 prime, x2 prime, y2 prime, z2 prime, comma t2 prime. Okay, and the difference, this is the time that this spaceship, the person sitting in spaceship will measure, and the person sitting in space station will measure this time. How do we relate them? It's very simple. We want to measure the prime times in terms of non-prime, so we use the Lorentz transformation because we know this time. So what I'll do is that I'll again very simply, t2 prime is, it will be gamma t2 minus v x2 over c square minus gamma t1 minus v x1 over c square. I'll take time terms common first, so it will be gamma t2 minus t1, and then what I'll do is that I'll club these other terms together. So gamma v over c square, it will be x1 minus x2. Note, we talked about co-local events, means x2 equal to x1 is equal to 0. So this term vanishes. So what I'll get is gamma t2 minus t1. t2 minus t1 is nothing but t, this thing. So I'll get gamma t. This is what I get, and this is what we have seen in the last slide here. T prime equal to gamma t. What is gamma? We know this is, sorry, my bad, this is gamma. Note that gamma will always be greater than 1, always be greater than 1, unless you're moving at speed of light, right? So gamma will always be greater than 1, right? Yeah, gamma will always be greater than 1, right? So this means the person moving in spaceship will measure a longer time, right? This is important. If you've seen this movie Interstellar, there the person, the gravity is also involved there, so it complicates things. But for our discussion, I'll say this, that the person who's traveling will see, they'll age less as compared to the person sitting on Earth, sitting in the space station. That is the same thing, that was same thing depicted in the movie Interstellar. So that was also based on this concept itself, right? Okay, one more thing I should have pointed out earlier. This is called proper time. When you measure any time in an object's rest frame, note that this object might be moving. So you measure proper time only in your frame. For instance, if I ask someone sitting in, let's say, Germany, what is the time right now? Okay. So they'll say that they maybe, I think the time is there 4:30 or something, right? Or 5:30, whatever. They'll say the time is 5:30 there. So for them, that is the proper time. For me, the proper time is 7:52, right? If I ask someone sitting in Bangladesh what is the time there, they will tell me the time there is 8:23. They're 30 minutes ahead of us, right? So that is the proper time. So this term keeps coming over and over again. Proper means you are measuring in their frame, in the object's frame. This is illustrated using this example, right? So I told you there's something, and nuclear physics and STR overlap. So again, this is the same thing. You see half-life, elementary particle, you'll see no. But as soon as you see C, most likely it will be a problem of STR, special theory of relativity. And again, the proper word is it just gives away that this is we are talking about relativity here. Again, I'll do the same things. We'll see that the frames are inertial. So there is one lab frame. Lab frame is nothing but that this is a nickname for rest frame. So again, this is a rest frame, which is S here, or we can call this lab frame in this case. And there is a particle, elementary particle. This is the subatomic particles and whatnot. Okay, so yeah, so it's moving in some, let's say, velocity, and now this is this particle's rest frame. This means, let's say this is moving with velocity v, right, which is given 0.9 c. this was given v equal to 0.9c. So ux equal to v essentially. Ux is equal to v. Then only this will be at rest. How? Let's see. Let's measure the velocity of this particle A in this frame. Okay, ux prime would be ux minus v over 1 minus ux v over c square. Ux is 0.9 c minus 0.9 c over 1 minus 0.9 into 0.9. So this will come out to be 0. This means this is the rest frame for this particle A. So we are sitting on the particle here. Remember in the first question that we discussed today, we are sitting on a photon. Similarly here we are sitting on this particle. So this particle will remain at rest in this frame. And here whatever time this particle will see, that will be the proper time. So this is it will see proper time, proper length, everything it will see proper. So proper is the term that we use when you are in your own rest frame. Note, actual rest frame is this, the lab frame, but in your rest frame you will measure proper time and proper length. Right, we will again see whether frames are inertial. Yes, one is lab frame, so inertial. Second is moving at 0.9 c, which is constant, so it is also inertial. What is the moving frame speed and direction? We know, we determined it to be 0.9 c using this, right? Because it has to be 0, so ux has to be, so v has to be equal to ux, then only ux prime will come out to be 0. What is the direction? Again I'll assume positive x. How many dimensions? Question is silent. I'll assume one dimension, which is the x dimension, right? And I'm assuming direction to be positive x here. So I'll again solve this problem. I'll say this is my lab frame. Here this particle was moving at ux equal to 0.9 c. This v is also equal to 0.9 c. This is the particle frame, right? And obviously the particle, let's name this particle A here. This particle A here is at rest. That's why this is the particle frame, right? And what we need to determine was so we were given proper half-life. Proper half-life was given as 5 into 10 to the power minus 8 seconds, and we need to determine the half-life. Sorry, we were given the half-life in lab frame. Okay, so we were given t equal to 5 into 10 to the power minus 8, and we are required to determine the proper half-life. Note, half-life is nothing but a unit of time. That's why we can use the formula for time dilation. So we know this formula, t prime equal to gamma t. Gamma would be 1 over 1 minus, am I making a mistake or something? No, t prime equal to gamma t. Okay. So gamma would be 1 minus v square. V square is 0.9 square c square over c square. This gets cancelled. T will plug in later. This will be 1 minus 0.81 into t. So this will be t minus square root of 0.19. So square root 0.19 is 0.435. So this is coming out to be 1 over t over 0.435, right? So what I'll get here is, I think I made a mistake somewhere. I don't know where.
So the proper time is primed or non-primed?
Proper time is primed, I think, because proper time you measure in your frame, or is it not?
Okay.
I'll confirm in the next class anyways. So yeah, so that's how you'll just plug in the values here. I'll revisit this because length contraction is also there. The concept of proper will come. I've hurried a bit in this class here, but we'll visit the same concept in the next class, right? The proper time and proper length, and we'll go a bit into that for the length contraction also. Yeah, so this is the length contraction. The concept remains similar. So we got observed length and proper length. There we had, in time dilation, we had observed time and proper time. So yeah, we'll see to this that we'll visit them again. So for now, if you have any doubts regarding velocity transformation that we had seen till here, you can just tell me. And time dilation and length contraction we'll cover in the next class, to lack of time today. Okay, so if you have any, I'm stopping the presentation now. If you have any comments, yeah, please go ahead. Rarely it happens that we finish on time. Today is the first class, I think. ठीक है. Did Netgate get sorry, Net date get released yet?
No, sir.
Looks like they're going to combine again. It's not fair, I think. Okay, okay. Let me post it. If you have any questions that you want to discuss in the class, you can email me. They need not be of GATE. They can be of other exam or from some textbook. Because sometimes GATE exams do not cover all the questions. I've seen some questions come in net, and similar questions are asked in GATE or just and other things like that. So it's good that you practice the questions from other exams also. Textbooks may not help, but for other exams definitely. So if you have any doubts, feel free to send me. We'll stop here at velocity transformation. In the next class we'll begin with time dilation, length contraction, and then we'll likely go into the energy terms which someone raised today. All right, so that's all from me.
Sir, the
Yeah,
formula which you used was right.
it was
Previous
correct.
question. Uh-huh.
Yeah, okay, that's what I'm saying, because I may have miscalculated something. It's fine. We'll again do it in the next class, because I don't want to hurry these topics. See, these are only one simple formula. The formula, the remembering the formula is not the problem. It's the concept that should be clear. So that's the whole aim of these sessions, and that's why I devote so much time to the theory part. The questions I can solve in, like, we can, even you can solve it in 2 minutes. Like, many people comment the answer right away as soon as the question comes on screen. So the idea is not to solve the question. The idea is to how to solve the question. That's why you see, where is it? I am, yeah, this pre-checks thing, right? This is the thing that I came into my that came to my mind, that what are some things that you must do in every question. Similarly, in the last cycle, when I did operational amplifiers, there also I had some pre-checks, right? That we must check these things. We must check whether it's an ideal, non-ideal situation, what to do if it's non-ideal. So these things helps, because when you are doing a problem, you revise the whole concept altogether. Every time you revise the concept of inertial frame, not accelerating, and again the number of dimensions keep on coming. So when you talk number of dimensions, you again remember there's x and y and z component, and that's how maybe these formula will come in handy, maybe not, I don't know. So but it's still, you revise the whole problem by just solving, you revise the whole concept by just solving one problem. So that's the idea. Anyways, we'll see time dilation, length contraction next class. I do not want to hurry just for the sake of solving a problem. We solve the problem, no, we'll visit it.
Sir, I was just thinking that if we
Mhm.
are in the frame which is moving at high speeds, then
Mhm.
comparable to light,
Mhm.
then means time will slower down for us.
Yeah, see, so that's
So,
that's the
so the
thing.
factor should come less than something.
Yeah, so the thing is that, as far as we know, we can't go faster than light. See, that was one of the very basic things that that's, if you remember the very first slide, I talked about the twin concepts. First was the laws of physics remain invariant. Second was speed of light is a constant. So the thing is, there is, theoretically, using this you can do that, but see, behind all this mathematical formula that we are studying, there are scientists who have talked about this question. So what you are arguing is that if we somehow we are able to move faster than light, then yes, we can see the future also. That's what you are arguing, I guess, right? Because you'll be moving faster, right? But we don't know whether we can move faster, and to be honest, I'm not equipped to undertake these discussions, because I have very limited knowledge of special theory of relativity. Because if you incorporate, that's why I told you, the movie Interstellar, which I mentioned, there they were not moving at speed of light, but they were close to a very large black hole. So there the laws of physics, there this again, this time dilation and length contraction came into picture. So I'm not trained enough, I'm not knowledgeable enough, sorry, to have this discussion with you. So I'll just say that there are people who talk about it on online forums, the people who write the papers. There are the talks do happen occasionally. But if you feel free, if you are interested, I highly encourage you to visit this question, and if you find something, please share with us. Or share with me. I'll put it in the class itself in some slide form or something.
Excuse me, sir.
Yeah.
Good evening, sir. Sir, what we have calculated in the question space.
Okay, let me share my slides again. Sorry. You're able to see, right?
Yes, sir.
Okay, spaceship. Where is it? Yeah, this one. So I'll define. So this was the problem given to us. So spaceship was traveling with constant velocity 0.7 c away from a space station. So first, let me draw the space station. This is the space station. We'll assume it's at rest. Okay, and it was given a spaceship is traveling with a velocity 0.7 c. So I'll assume this is a spaceship. It's traveling with a velocity of 0.7 c in this direction, right? And it says that, so inside, you see spaceship, you must have seen in some TV movies or something. Spaceship is a very huge compartment, right? So there are people inside, the component inside. So sometimes they release a probe is nothing but a anything experimental device. They can be small, it can be big, but for our purposes we'll say this is the probe. And it says that a person in this spaceship ejected this probe. Means, so what I'll do is that I'll draw this. So this is the spaceship. So this is the space station. This is the space station. This is a spaceship. What it did, it ejected. So spaceship was traveling in this direction at 0.7 c. What this spaceship did, it ejected a probe, a very small probes for some experiments in this direction, and the velocity as measured by spaceship, it said that this probe velocity was 0.59 c in this negative x direction. So let's say minus 0.59 c. So here the velocity of this probe ux prime is minus 0.59 c. The question asked, now the space station, a person is sitting here also, right? So this person saw this, that a probe is ejected. Now this person wants to know what is the velocity of this probe as per their measurement, right? So they must have some way to measure, some sensors to sense their the motion of this probe. So they want to know what is the velocity of this probe and direction of this probe. So that's what the question is asking. So person is space station, this person sitting here would see the probe moving at speed xc. So this person sees that this probe is moving at this speed, which we call ux. This is our notation, no primes, at the speed xc, right? So this was the frame, this was the frame of reference of this spaceship. But this probe will also have some ux velocity, the same probe, one velocity measured with respect to spaceship, the other velocity ux respect to space station, and we need to find the value of ux. Ux is xc, so we find the value of ux in terms of c, we'll get the value of x. So that's what we did, and we used this, we did this analysis here. So we know ux. Yeah, is it okay now?
Yes, sir.
Okay, good. Yeah, so stop presenting. Yeah, any other comments, any other questions, please feel free. Not necessarily str related. If I know, I'll answer. Yeah. Okay, if no comments, then we'll close the session for today. Thank you for your time.
Thank you, sir.
Thank you for listening. Have a good night. Stay safe. Bye bye.
Thank you, sir.
Welcome everyone.